Okay, so let's get started for today's class. Our today's class is on logistic regression. And even though the name is looks like it's a regression algorithm, but it's a misnomer. It's actually used for classification. So today we'll be going over logistic regression and we'll be solving some classification problem using the same data set that we were working on yesterday as well. And what we studied, let me just revise on what did we study yesterday. And we might not need the entire 2 hours of the class today because a lot of what we have studied yesterday, that will build a solid foundation for us today. And if you got everything yesterday, today will be much more easier. So that's the reason I'll be revising a lot of things from yesterday, because that will be your basic foundations going ahead in the supervised machine learning module as well. We'll see how we can use logistic regression for classification. Until now, we have been doing regression algorithms which were used for, or maybe we were using a linear regression model for regression problems, right? So we'll be seeing how we could use logistic regression today to solve classification problems as well. And then we'll obviously go ahead and implement it in Python, just like we did yesterday. Yesterday, we were using gradient descent to solve a regression problem. Today, we'll use the same gradient descent algorithm to solve a classification problem using our logistic regression classifier. So let's recap what we have seen until now. We had, yesterday, we were solving a regression problem where we had a bunch of data points. And our objective was finding the line which was closest to all these points. And we said finding a line is equivalent to finding the M and B, right? Because if we know what M and B is, we know what that line looks like. And we want to do it in a way that results in the least error, right? So what was the solution then? We said what you could do is, let's start off with a random line. And with that random line, we'll have some random error. Right, with the random set of M and B, we'll get random set of errors that are generated. And now what we need to do is adjust this line such that M and B reduces, or we need to adjust the M and B such that the error reduces. Okay, and that was the whole suspense of yesterday's class, wherein we were trying to find, let me get my pen over here. So the whole point of yesterday's class on what we were trying to do was, I'm trying to see why I can't get the stencil up over here. Give me 1 second. Okay, this is better now. So what we were trying to do is we were trying to find delta M, right? Because we knew that if we adjust M equals to delta M plus M, right? So we need to adjust the M such that the error reduces. So the whole point of yesterday's class was finding this delta M and delta B, right? So because B was delta B plus B. And can someone give me the equation for delta M? What did we derive from yesterday's class? And we'll quickly go over that derivation as well. But can you recall what this delta M was equal to from yesterday? What did we see? Do you guys remember? What did we derive delta M to be? Yeah, so first of all, tell me what intuitively, what did we said? That both of these should depend on what? Because, yeah, so both of you got the final answer right over there, but intuitively, what did we say? How did we arrive over here? Where did we start with? We said that both delta M and delta B should be dependent on error, right? Somehow, because based on how much error we are getting, we'll adjust the M accordingly, right? So both of them kind of depend on error. Based on the derivation, we took the gradient of the loss function over here. And what we saw was delta m, we took the partial derivative with respect to m and then partial derivative with respect to b. And what we saw was delta m was equal to error times x, right? And we had some constant term over here as well. And this was again some constant term times just the error, right? So this is what we saw yesterday. And did we use delta m and delta b directly over here? Or did we have to do something with, did we use the gradients directly, or did we have to do something with the gradients? Yeah, multiply by a small learning rate, right? So we had to multiply by the small learning rate. And should we go in the same direction as the gradients or in the opposite direction as the gradient? So if the gradient is positive over here, if the slope of this line is positive, should we go in the same direction or the opposite direction? We need to go in the opposite direction, right? So that's why we can also multiply this with -1. So if this is -1, then we are assured that now we'll move in the opposite direction of the gradients. Okay, so this is what we have seen yesterday. And we'll do this thing until we converge. So in our case, we said that we'll run this same gradient descent algorithm multiple times so that we eventually converge to a minima. And here's the derivation that we saw yesterday. We started off with the mean squared error, right? So we started off with mean square error. We said that mean squared error was estimate minus actual the whole square. And this is also the cost function over here. This is mx plus b minus yi, because if you have the estimates over here, we'll be predicting using the linear model, which is mx plus b, and this is actual is the yth I. This is the true y, right? And this is the predictions. So this is predicted, and this is the actual. Right? Then we said you can also represent that in terms of if you plot it on a chart, the graph of the loss cost function would look something like this. For a random error, we'll get a point somewhere over here on the chart, on the graph over here. And for this particular point, now we are interested in whether we should move towards the left or whether we should move towards the right, right? So which direction do we need to move? And that we could do by taking a derivative at that point. So if I take derivative at that particular point with respect to m, so if I do the partial derivative of j theta with m, I'll get the derivative, I'll get the delta m, and I need to move in the opposite direction of delta m. So I'll multiply that by -1. B was delta b, take the derivative, and here's how we went about taking the derivative. We applied the chain rule, and this is what we got in the delta m. And similarly, you could do for delta b as well. Over here, everything remained the same. The only thing was mx plus b minus y, everything else was constant. And because d by dx, x is 1, so d by db, b was 1. Over here, can you tell me what is constant and what is not constant? I told you yesterday. So in this case, let's say when I am taking, for this particular solution, I have x, y, m, b. So which are the constants and which are the variables? Yeah, the x, y, and the b are the constants. The variable is m, right? Because we are doing a partial derivative with respect to m, we are assuming that b is constant. And why is x and y also a constant? Generally, when we are doing calculus in high school, or we generally have x and y as the variables. But why is x and y a constant over here? So Sudipto, not necessarily just because we are doing d by dx or d by dy, not necessarily just because of that, but the thing is we are doing it for one particular point. For a given pair of xi comma yi, we are trying to find the delta m and delta b at that point. And that's the reason xi and yi are the constants. Does that make sense? So Nitish, you pretty much covered what I just said over there. I just want to make Sudipta, you got it as well. Okay, great. All right. So this is pretty much what we have seen yesterday. All right. Just wanted to make sure that that was fresh in your head. And then we saw the effect of learning rates on our algorithm as well, right? So with a large learning rate, you have a chance that you might just overshoot and you never reach to this target over here, right? Because if you take the gradient of that point and if your learning rate is too high, you might adjust, you might just go too much towards this direction. Rather than just taking a small step on this graph, you might just go too much and you eventually overshoot. And no, that's what we seen in our experiments as well. With a smaller learning rate, you are generally guaranteed that you will reach to your minima somehow. But again, you don't want to be so, you don't want to select such a small running rate that it takes you forever to reach to this point, and you, after even 100 iterations, you don't get close to your best answer, right? So there is always a trade-off between the choice of learning rate. And then no, this is the same thing that I'm showing you. This is the global cost minima, right? And over here we are seeing that this is a nice convex function, but a lot of times, in machine learning, we'll also see that you will have functions which are like this, which is not convex, right? So if this is not a convex function, this means that there are a lot of local minimas as well, right? If you take a learning rate which is very small as well, and then what might happen is you might get stuck in the local minima over here. So your algorithm might think that I have reached to a minima, but it is not actually a global minima. So this is a local minima then. So with gradient descent, you are not always guaranteed to reach to this global minimum if your error function is not convex. So that is something that you must know. Gradient descent algorithm will always work if you have a j omega, or the cost function that you are selecting, which is a convex function. Does that make sense? All right. So let's see. Now we are gonna see how we can do classification as well. But so Nitesh says, can we make our algorithm smart enough to stop itself when it reach to slope 0? Yes, absolutely. We could do that. If you reach to a point where you have a minima over here, and again, you won't always have a slope 0 as such, right? If you will all know, when you try it in your experiments as well with the data set that you have yesterday, you will never get a absolute 0. It will be something like, you'll get a error which is like 0.003 and so on. So how do you, what kind of threshold do you set? Do you set it as 0.0003, 0.0005, or what do you want, right? So you can't be really sure on what number do you want to fix at. And that's why what most people do is, rather than trying to find put it a threshold over here at where to stop, they say, I'm going to do this iteration for, let's say, 100 times, right? And whatever that is, whatever answer I get, I'll just stop over there. That way you're guaranteed that your the slope will the slope won't shift to negative as such. If it is shifting to negative, then maybe you're going over here then. right? Because then that's a function of learning rate. So if your learning rate is too small, then you reach over here. If your learning rate is too high, you might jump over here as well. But after a point, it doesn't make a lot of difference, because this is how your error function would look like. So this is how, if you plot the total error or your error, it should look something like this, right? So if you plot your loss, it should have something, a curve like this one, right? So this is your loss. So your loss will eventually tend to 0, but it will never actually reach 0. It tends to 0 with as you go on, increase the number of iterations. As n increases, the number of iterations increases, your loss tends to 0. It's difficult to get it absolutely to 0. And in a lot of machine learning problems, you don't want your loss always to be 0 as well. Let me give you an intuition why that could be. So let's say I have a curve like this, okay? And I try to, I'm not talking about just a linear regression model, but just any model in general, okay? So what should be my prediction be for this point somewhere over here? So let's say I want to, let me take another color over here. So remember, this loss over here is the error that we are seeing, the total error that we are seeing between all these points, okay? And this is what the model looks like right now, okay? But what happens if I have one outlier? Let's say there is one X over here, which is somewhere over here, okay? Do I want my model? Let's say I don't necessarily always have a linear model. I can also have a non-linear model. So is it ideal for me to draw a line something like this? The second line that I drew, the curvy line, or the first line is better? So I hope you are able to see that properly, the lines, and if it is difficult, let me know. So Sudipto says first one. Nitish, what do you think? Is the first curve the fit better or the second fit better? Yeah, so let me make sure that I do it once again. So let's say we have our points over here. So these are our points, right? So, and there is one outlier somewhere over here, and I'm trying to fit a linear regression model. I'm trying to answer your question on why don't we always absolutely need the loss to be absolute 0. That is not a well-intended behavior as well, to get the loss as absolute 0. And let me give an intuition why, right? So this is, let's say this is the first model that I drew, which was kind of fitting the trend over here, right? Or maybe somewhere over here as well, okay? And here's the second model, okay, which is kind of non-linear as well, but tries to follow all the axes. So it is trying to get through all the axes, and we are trying to get error very close to 0. Okay, so which one do you think is a better model, the first one or the second one? And what's the intuition behind that? Why do both of you think that it's the first? Oh, in the first one you will get more error, right? So because the difference between this X and this line will be more, the error will be more in the first model. The second model, error will be less. And now Nitish, you think that it's the second one because the error is less. Is that your intuition? So how do we draw that? So Nitish, how did we draw this line? Let's say we were doing linear regression. So what equation did we use for the linear regression? Mx plus b, right? So this was a linear equation because you just have x raised to 1 over here. If you add more complex terms, let's say you say m x square plus z x raised to 4, you will start getting more complex curves like these. Okay, if you try to fit more parameters to more complex no, orders of 4 and 3 and so on, you will start getting more complex curves. So my question was, why do I, so I'm saying that the right answer is the first one is a better model, because what is the purpose of our drawing this line? What was the purpose of us trying to fit it? Why are we doing this in the first place? Why are we creating this model in the first place? What was the whole purpose of creating this line? Is it to get the error 0, or is it something else? If it is if the purpose was to get error as 0, then definitely the second one was a better option, because error is close to 0 over there. But is the purpose of for us drawing the model is to get error 0, or is it something else? And what is that, Nitesh? What is the purpose? Why are we doing machine learning? Why do we create the model? Well, we are creating the model to make the predictions. Exactly. So over here, when I'm saying that there is only one outlier over here, will the first line do better in the test phase, or this line? So in the test phase, most of my x's are on along the straight line. So the general model of the world, the purpose of machine learning is to build a generalized model, and not no model which fits perfectly in just the training phase. So over here, this is also called as overfitting. Okay, you don't want to do that. As a machine learning engineer, one of the biggest challenges that you have is you might overfit your model during the training phase. You might say that I am getting 100% results during the training phase. My model works 100% of times. But well, that doesn't help, because that is of no value to us if it fails miserably during the test phase, if your test accuracy is only 0%, or maybe let's say 30% or so. Okay, does everyone understand why are we why this would be a better fit over here, and why don't we intuitively want error to be always complete 0 as well? Because if the error is always 0, then you are kind of overfitting during the test phase itself. You want your error to be less, that is not a question. But if you are getting as an absolute 0, then there is a good chance that you are drawing a model which is is fitting all these points. And again, this is also a universal approximation. There is a theorem that we are going to study during neural networks as well, which says that given a set of points, okay, there always exists a n-dimensional model which will always have a perfect fit over here. Okay, given a set of points, you can always come up with something like ax0 plus bx1 square plus cx2 square plus dx4 cube and so on. Okay, irrespective of the model you have. So Sudipto says, what if the function itself is a polynomial and follows the same trend? So what function are we talking about, Sudipto? Can you please elaborate your point? So which function are we talking about? So higher order functions, but where is the function? Over here, these are just a set of points. And what function are we talking now? We are building a model. What I'm saying is there is a theorem, which is a universal approximation theorem, which says that given a set of points, you can always come up with a line which will perfectly fit all these points. well, then in that case, you will just have this coefficient as 0. If that coefficient is 0, that term is gone. So a general equation, like if you have ax 0 or ax raised to 0 plus bx raised to 1 plus cx raised to 2, if you have n number of polynomials that you try to fit with, then you can always come up with the best fit to all these points. Okay, but the problem is just fitting all the training points is not a good answer to the challenge that we're trying to solve. Okay, you might just as well just write a bunch of if else statements, right? That will do the same thing. If you just write a bunch of if else statement, it will exactly fit all your training points. If this is this, then do this. If this is this, then do this, right? And that's not what we want. We want to come up with a general model which gives a sense of how this data is spread across. So Sudipta, I'm not sure if I answered your question over there. Did I answer your question? So you're saying that if the equation is the form of mx plus b, but we actually have mx square plus bx plus c. What I'm saying is this is not guaranteed that this will always fit. This is just the first order term, right? This is just a linear model. This can't fit all the x's. But what I'm saying is if you have a general model of term ax 0 raised to or ax raised to 0 plus bx raised to 1 plus cx raised to 2 and so on with n number of polynomials or the order of x, then you can always fit any x which is given. Does that make sense? And you can try it out yourself as well, and we'll do it when we are doing neural networks. We'll see why that is there, because it is also related to digital logic design, and somehow I'll connect the dots for you. This is, if you put together this equation, it will resemble, have you heard of universal gates? With universal gates, you can approximate any function, right? So it is of that form. We'll see when we go into neural networks. Okay. All right. So having said that, we took quite a detour over there. I was trying to explain why it's not necessarily that we are trying to get error as always absolute 0, but we want to reduce the training error as little as we can. All right, so the question now is, can we use linear regression for classification? Well, we already have a good model of the world. So let me go ahead and draw this. So let's say we again have this. Over in the example that we did today, we are going to go over the student scores and whether they pass or fail on an exam. So this is the result, whether they pass or fail. Let's say we have given a student the distribution of the pass and the fail score looks something like this. So these are the people who have failed, right? And these are the, this could be something, these are the students who have passed. Okay. So this is how the scores and the result look like. So if the score is less, right? So after a certain point, they pass, right? So let's say if the passing score was 37 marks or 40 marks, then after that, everyone has passed. So result is 1 over here. Let's say the result is 1 for pass and 0 for fail. Okay. So we already know that we can do a linear regression model on these points. So if I have a linear regression model with this data point, can you give me a sense of how that line might look like with these set of training points? Pass and 0 for fail. Okay. So let's see if we try to fit a linear regression model. You thought that it would draw a straight line, and what I said was that wouldn't be the case, because as soon as you draw a straight line in the next iteration of your gradient descent, your line will try to get closer to all these points, right? So you might end up with a line like this, which is trying to get closest to all these points and trying to reduce the error. Okay. So one algorithm that we can think of, can you think of a very simple algorithm based on which you can still do classification problems using linear regression. So let's say this is somewhere in between 0.5 over here. Okay, and this is the output y equals to mx plus b. What kind of simple algorithm can you think in your head to still use linear regression for classification problems? So the output now, instead of having a continuous value, we want the output can be only 1 or 0. Can you think of an algorithm, a simple rule that we can still use over here? Yeah, so now if the y prediction, so we could write a simple algorithm such that, now let's say if the predicted value, if the prediction is greater than 0.5, then say the result as the output as 1, or if it is less than 0.5, we can say output as 0, right? So we can simply do that. So why not just use this to know, rather than trying to come up with some other form? We already know how to work with linear regression, so let's use this to do classification problems as well. Well, there is one challenge with this approach. Let me show you what. So let's say if now I have some more points over here which have a lot of high points. Okay, ideally it shouldn't matter to us whether there are less students or more students who have more marks, right? Our approach should remain the same. But what will happen to the linear regression line if we have a lot of more these points? Can you think how the line will shift if we keep adding more points towards the right over here? Can you think of how the linear regression line would change? Yeah, it will shift towards the right, correct? So because it will try to get closest to all the points which are possible, the next line might have something like this. Okay, it will start getting more and more flat. Okay, as and when you keep on adding more points over here, right? And what could be a problem now? Will the same 0.5 threshold work now? No, right? Because if you have more points now, you will end up misclassifying all these points, right? Because for this x, the output will be still less than 0.5. So all these points now will start getting misclassified. So all these will be misclassified as 0, as fail, rather than the actual result which should have been pass for these case, right? So does everyone understand a problem with this approach of using linear regression with some kind of threshold? On why that not be an ideal case? Because when you keep on adding more zeros, ideally it shouldn't matter, but what would happen is your linear regression line will keep on shifting towards uh, the outliers as such, and that is not an expected behavior from your system. So do you understand why that might be a challenge? Okay, so I see a yes. I hope it was for the same question. All right, so that is one thing. The other thing is, in terms of interpretation of the output as well. So let's say, what is the range of the y prediction? What is the range of the y prediction? Or no, let me rather say, no, y prediction. What is the range of values that you get with y equals to mx plus b? So guys, my question is pretty simple. What is the range of y is mx plus b? Mx plus b is a line. And what is the range of a line? So Sudipta, I'll come to that comment later. Okay. And you can tell me if what we will do next is similar to what you thought. So here's my question to you. What do you think is the range of Y prediction with a linear regression model? The value of Y, no, with the linear regression model. What is the range of Y with linear regression model, the Y predictions? This is your Y target or the Y actual, right? What is Y prediction? These are the predicted values which are all of your model. So your predictions with the linear regression, do you agree that it will go from minus infinity to plus infinity? Right? And what you're trying to do is interpret that as in terms of whether it is a 1 or a 0. Right? And that's a challenge over here, because what does having a large number over here mean? So does that mean that it is very close to no 1? So does that mean that if I get Y prediction as 100, that means that is it equal to having a strong 1, that I'm sure that this person is going to pass? Or does that mean equals to strong 0 if it is if it is negative infinity? I don't think so. You can't say for sure that just because you have getting a large number over here, that means it's a true case, or no, the probability of it being 1 is large. Okay, so that is not the case with linear regression. How do you interpret this scale of minus infinity to infinity, whereas you are trying to do something which is no, you're trying to see whether it is in class 1 or class 0. Okay, so these are the two challenges that are generally put out when you talk in terms of linear regression and trying to use it for classification or problems, because over here you are more interested in what is the probability of this point lying in the student passing and failing, whereas with linear regression alone, what you are trying to do is just just threshold the values at certain point, right? You're just thresholding it with linear regression to try to make it to classification. Okay, so what can we do about this? Is there a solution, or is there a simple thing that we can think of rather than trying to draw a line over here? What if we drew something like this? What if we had a sigmoid over here rather than trying to fit a linear model y equals to mx? What if I tell you that this model, this shape will work much better if I have something like this, which after a certain point automatically gets threshold. So irrespective of how many outliers you add on these sides, on any side, the eventual output doesn't matter. So the sigmoid, or the model, the red model that I'm drawing, is a sigmoid function, which is an S-shaped curve. Okay, so rather than drawing a straight line, what if we try to fit this model? Do you think that this will work much better? So 0, 1, and here's the equation of this model. So instead of doing y equals to mx plus b, if we have a model of this form, do you think it will work much better just intuitively? Because if you try to add more points over here, if you add more black points or more rounds over here or more x's towards this side, will the output change? The output will still remain the same, right? And that is the intuition behind using logistic regression. Okay, so what we do in logistic regression is, again, we'll start off with the same linear model. So we'll start off with saying, no, using y equals to mx over here, right? So we'll still use a linear model, a linear combination of models over here, or the linear combination of features. So we'll still start off with, we'll still have the features that we have. So x1, x2, and I'll shortly explain where is this x1, x2, x3 coming from. Over here, we are just looking in one dimension over here where there is only one x1, and this is the output that you are trying to get. But generally, you will have a lot more features when we are working with machine learning, because that's the power of machine learning. If you just have one feature, then you might rather just do it using if-else conditions, right? But with more features, as you keep on increasing more features, your machine learning models will be able to generalize well as well. Okay, so if you have more features, you'll still be using a lot, summation, of the input features over here. So you'll still use y equals to mx as a linear combination of features, but we'll also add another block over here, which is the sigmoid function, which will transform our linear model. So something that we had a linear model, will transform it to an S-shaped curve. Okay, so we'll transform the linear model to an S-shaped curve to fit our needs. Okay, so let me go ahead and let's do some mathematical formulation of the problem that we are trying to solve, just like we were trying to do yesterday. We'll try to formalize this problem, and this is a trend that we'll be doing for a lot of other classes as well going ahead in the our course. What we'll do is first try to understand the theory and the concepts behind it. Okay, we'll try to get an intuition behind how that problem is working. Right now I gave you an intuition why that S-shaped curve will work. Next, we'll do a mathematical formulation of that problem, so that I don't know you at the end of the class, you are not an engineer who just knows how to use scikit-learn models, but you also understand the math behind it. And the third step will be to go in and do that in Python. Okay, so there are a lot of classes and there are a lot of courses online which will teach you either one of them. Either there are some courses like Andrew Ng's the Coursera's machine learning course, which will talk a lot of theory, and there are also a lot of videos and courses which will talk only about implementation. But what I want to do is build a course which will give you the solid foundation in the math behind these concepts. First give you the intuition why that will work, then give you the math, and then do the implementation. So that's the approach that I'm taking with all these classes, just so that you know what to expect in the lecture. In the class going ahead as well, in today and yesterday's class, what we saw was, first we got some intuition on why something would work, then we'll do the mathematical formulation, and then we'll implement it in Python. Okay, so I hope everyone is with me on that approach, and if there is something that you would like to be changed, please feel free to connect with me and explain what's your take. All right, so let's do some formulation on what will be the output equation of our model over here, or the model that we are trying to draw. So again, let's draw the classification problem that we had. So the x's and the zeros. So what we will first do is first try to come up with the same linear model that we had last time. Okay, so the output was in the form y equals to, or let me write y equals to b plus mx. Okay, I'm writing the same thing, just writing the b before. Okay, so can I also write this as, now I'm just changing the notation over here, and the reason for doing that is, as I said yesterday, when you go and read things online, you might see this notation. When you see other videos, you might see this notation. When you read Andrew Ng's Coursera course, you will see this notation, and in the books as well. So you might think that you don't know this stuff, and it might seem very cryptic to you, and that's the reason I'm showing you the notation which they use as well. So instead of saying y equals to b plus mx, what you would see mostly when people are trying to do this in machine learning world, they would use a parameter vector over here. So rather than saying b equals to mx, we use saying theta 0 plus theta 1 times x. Okay, this is same as the same constant over here. The m is the theta 1 over here, and so on. Okay, now this was in one dimension. So when you have one feature, you have this form. If you have more than one feature, what kind of equation will we get? So we'll have theta 0 plus theta 1 x plus theta 2 x and so on. Okay, and this is x1, this is x2, and so on. And note that I'm not adding squares and cubes over here on the it is still a linear model. It is still a linear combination of input features. So this was x1 and this is the output. This is still a linear combination of theta 0, theta 1 and x. Okay, there is no squares or cubes in this equation right now. Is everyone following until over here? On what I have done, I'm just changing the notation from b equal to mx to theta 0, theta 1 and so on. All right, so in the matrix form, can I also write it like this? Can I also write it like this? Y equals to theta 0, theta 1, theta 2, so on, multiplied by x1, x2, x3 and so on. Can I write it like this? Does everyone agree? Okay, so which in turn could be written as y equals to theta transpose x, dot product of theta transpose. Theta transpose is nothing but the same vector which is now kept vertically over here, because it has to be of the same shape to get multiplied with x. So theta transpose times x. This is the equation for linear regression in matrix form. So Nitesh says the 0 shouldn't be there, right? So which 0 are we talking about? Theta 0. Okay, so why do you think theta 0 shouldn't be there over here? So you mean this should be theta 0 plus theta 1 x1 plus theta 2 x2 and so on. Yeah, so what I'm saying is essentially over here, if you imagine if x1 was 0 or if x1 was 1, then what would happen? If x1 is 1, if you say that, can I write it at like this? Right, so if I have a vector x which is always starts with a linear combination of ones, so I can also write this as, instead of saying theta 0, I should have said theta 0 x raised to 0 plus theta 1 x raised to 1 and so on, and then say theta 0 theta 1 and so on, multiplied with x raised to 0 plus x1 plus x2 and so on. Now will that work? Okay, so it's just the notation over there. Okay, so that gives us y is theta times x, theta transpose times x. That is the linear regression in matrix form. All right, and what I said was, now let's create a new page for over here so that we have some more space. So let me create a new page over here so that I don't crowd the slide over here. All right, so now you know that for the linear regression form, we have y equals to theta transpose x. Just wanted to make sure, how did we get this, or why are we using this? All right, so what I said was, with logistic regression, what we are going to do is still use, now you'll understand this notation much more better when I said, now what do I mean by linear combination of inputs? So I have x1, x2, x3, and times theta 0, theta 1, theta 2, or maybe x1 is times theta 1 always, right? So x2 is theta 2 always, theta 3, and theta 0 is just the offset, right? So theta 0 is added over here maybe. So this will give us theta 0 plus the same equation that we just wrote, right? So this is linear regression, and what we are going to do is add a sigmoid block over here, which will convert our linear model and threshold it to have a nice S-shaped curve like this, right? And what was the equation for the sigmoid? We know that the equation for the sigmoid, this S-shaped curve, is g of z is 1 upon 1 plus e raised to minus z. Okay. If you want to know where is this coming from, 1 upon e raised to minus z. So what will be the value of gz if z is tending to infinity? What will be the value of gz? So as this is z, this is gz. If you put it in this equation, as z tends to infinity in this direction, what is the value of g of z? Put z in this equation. As z tends to infinity, g of z will be e raised to infinity, anything raised to infinity over there, e raised to minus infinity. E raised to minus infinity will give us 0, right? And 1 upon 1, that will give us 1, right? So that's why we have, as z tends to 0, g of z is 1. And as e tends to 0, what will be the output? As e tends to minus infinity, or let me say, as z over here tends to minus infinity, what will be the output? If z tends to minus infinity over here, yeah, as e, if you put minus of minus infinity, that will be positive infinity. E raised to positive infinity will give us, what will be that be? That will give us, that total thing will be e raised to minus infinity should give us 0, right? This e raised to positive infinity, e raised to minus infinity will give us minus 1. So 1 minus, I'm getting confused over here. Sudipto or Nitesh, can you help me out? Why are we getting e raised to minus? So if I said 1 plus e raised to minus of minus infinity, how do I solve this? So it should tend to 0. That's what it is from the curve over here. But why are we not getting it? To get it to 0, okay, so it will be 1 divided by infinity. Yeah. So 1 plus e raised to infinity. Now this is again 1 plus, 1 plus is again e raised to infinity is infinity. So this is 1 divided by infinity, that will tend to 0. Okay, does that make sense? Okay, so I think Himanshu just joined in as well. So Himanshu, you missed a lot of good stuff, I guess, in the beginning of the class over here. But we are trying to formulate the equation for logistic regression on what the output of the logistic regression should be. All right, so this is the general form of the g of z, which is 1 upon 1 plus e raised to minus infinity. So if you pass this output, the y, this is the y over here. If you pass it through uh, g of z now, what should happen? So if you say g of y now, what should that be? Yeah, that is correct. The graph over here should be, it will cut the y-axis at 0.5 over here. Okay. To just make it, this was not the y-axis as such. I was trying to make sure that I show the S-shaped curve properly to you. Okay. So I want to make sure that this is not just the y-axis that I was trying to plot, but I was trying to show the general shape of the curve over here. And it should pass through 0.5 over here. All right. So what should be g of y now? If g of z is 1 upon 1 plus e raised to minus z, then what should be g of y? So here's how this block works. So think of it as, as I drew before, this is how that block is working. I gave you the y is this. So what should be the output of this block? It is pretty straightforward. Yeah, so if g of z is this, then if I want g of y, then the output should be 1 upon 1 plus e raised to, instead of z over here, we are substituting y. So, and what is y? Y is theta transpose z, e raised to minus theta transpose x. Okay. So this is the model that we are going to use, and this is how we are going to try to come up with the logistic regression model. Is we'll use this equation. We'll first use the same linear regression model to combine all our feature vectors, and then we'll pass it through a S-shaped curve to get 1 plus e raised to minus theta transpose x. So everyone with me on the output that we are trying to get from our logistic regression model? So the only thing that, and the reason why this is so important as well, is this is also happens to be the building block of our neural networks. So whenever we go into neural networks, we'll see that every neuron is nothing but the model that we just built. So every neuron, when someone says that I'm building a neural network, they have something like this structure which is connected, right? And each neuron over here is nothing but one logistic regression block. Okay. So the same thing, the same math that we just saw, it will apply to neural networks as well. All right, so let's go ahead and try to do this in Python. We already know what the equation of g of y should be. We have, just like we were doing yesterday, we'll go to Azure Notebooks, we'll work with the same data set, and we'll try to do classification task on it. Okay. All right, so let's go ahead and implement this in Python. All right, so let me make sure that I am signed out and signed in again. All right, so let's create a new project over here. I'm going to create a new project, Logistic Regression. We'll make it public. And it would be a good idea to have whatever we did yesterday as open next to us for reference if you want to look at it. So if you want, you can go ahead and open up your yesterday's notebook as well, because a lot of steps will be similar. Let me know once you are ready with your notebooks created. All right, and let's also open up our yesterday's project so that we have that as a reference for us. All right, so let's go ahead and get the data set that we were using yesterday as well. So this is the same line that I had yesterday. Go ahead and do that, do the same thing again over here. Let's also get the same data set in our logistic regression notebook. So I have the data set ready. I'm gonna go ahead and read it in the, I'm gonna use the same libraries that we were using yesterday as well. And then I'm gonna go ahead and read it in my data frame. And let me know once you are over here. All right, so can you go ahead and plot out the, now this time I want you to plot out hours and the pass no classification, because you're trying to do a classification task. So I want you to plot the data frame of hours and whether the student has passed or a failed. Can you go ahead and try to visualize it? So complete it and let me know in the chat box. I want you to visualize the hours and the pass variable over here. So we should be able to look at the hours and say whether the student has passed or a fail. All right, so let me go ahead and do that as well. So I'm just gonna go over here and first separate out my X and the Y. So I'm gonna on X axis, I need the hours, and on the Y axis, I'm gonna use the pass or a fail, okay? All right, so I'm gonna use the inherent or inbuilt methods from the data frame itself. I'm gonna say data frame.plot. You can do it using matplotlib as well. And internally it uses matplotlib anyways. But I'm gonna use the scatter plot over here so that I know I can see the scores over there, right? So I'm gonna use the scatter plot. On X-axis, I need the hours. On Y-axis, I'm gonna use the pass or a fail. And for the colors, I'm also going to use colors over here so that it is very clear to us whether they have passed or failed. So I'm going to use, again, for the colors as well, I'm going to use pass or fail. Again, you don't have to really do it, but it's just that just make for the visual purpose I'm doing it. Okay, there is no reason for us to explicitly plot the colors as well. So the colors will become important if you're trying to do it in more than 2 dimensions. Like right now we just have 2 dimensions, but if you want to have two features, x1, x2, and then the third variable as the pass, which are shown in the color, then it becomes important. Right now we have only hours over here, so it doesn't make really sense for us to draw the colors as well. But if you have more than two features, then or more than one feature, then definitely you need to use colors. Okay, so I've got a plot like this one, which is now all the blue points are the students who have failed, and all the red points are the students that they have passed. Okay, so this is how our data is laid out. So seems like after you have studied more than 4 hours, you can pass your exam. So generally that looks like the trend. Okay. All right, so now that we have this over here, let's go ahead and do the same thing that we did yesterday. Yesterday we were building the gradient descent algorithm for our machine learning, and we're trying to do linear regression over there, right? So this time we'll do the same thing, but we'll try to use a logistic regression equation that we just derived. Okay. So again, same thing that we were doing yesterday. I'll start off with m as 0 and b as 0 as our coefficients, initial parameters to start off with. And then I'm going to start defining my function logistic regression. And again, this time, if you look over here, here's what we did for linear regression with gradient descent. We had all x's, all y's, and m comma b. So similarly, again, I have x this time, y this time, or I can again say all x, all y, and the m and the b. Okay. Same thing, nothing new that I'm doing. And again, we can use the same format that we were doing yesterday as well. We need the for x comma y in zip all, right? So I'm going to copy the same thing again over here. Let's copy it and paste it over here. So I'm doing the same thing for x comma y in zip all x comma all y. Y prediction is mx plus b. Now what should I change it to? Now this time y prediction is not mx plus b, but here's the equation that we have derived. So what is the output of logistic regression? Now that is very difficult for us to find out over here in this slide, definitely. So let me write it over here for you. So here's what we said the output of logistic regression should be is y should be equal to g of theta transpose x, which should be equal to 1 upon 1 plus e raised to minus theta transpose x. So this is just like we had y equals to mx plus b. Now with logistic regression, we have this form. So can you think of how can we do this? How can we implement this equation for our y prediction in the code over there? Can you go ahead and try to do that? And what is theta over here? Well, right now we have only m, x, and b, right? So this is same as 1 upon 1 plus e raised to minus mx plus b. Okay, because theta, remember, is just a parameter vector of b and m over here. So it is just mx plus b. So can you implement this equation over there instead of y equals to mx plus b? Now this time we have y equals to 1 upon 1 plus e raised to minus mx plus b. And to give you a hint, what you should do over here is define a new function first. So let's go ahead and define a new method first. Okay, because it won't come very intuitively to you to do this. So first let's define a new method which will give us a sigmoid of anything that we give. Okay, so this method that we write, so let's say define sigmoid. Now it takes in any input that you give, and it should return the sigmoid of that value, or the e raised to z that we just defined, right? So I'm trying to get only this g of z. So anything that we give that input, it should return 1 upon 1 plus e raised to minus that number. So can you go ahead and try to do this? What should this return number be? So all I want to do is anything that I give as input, I want to return 1 upon 1 plus e raised to minus that number. Can we do that? So Sudipto, that whatever you have done should work. Just make sure that the exponential method that you are using, uh, is it a natural base e or what that is? So guys, seems like the screen is not clear over there. So just give it a few seconds. It should become clear in a few seconds. So guys, I want you to find what this return value, how will you return 1 upon 1 plus e raised to minus z? Yeah, that should work as well. And to give you a hint, NumPy has a implementation of e raised to a number as well. So can you look for a NumPy method as well? That will be much easier. So guys, again, my ask from you is define a method that returns 1 upon 1 plus e raised to minus that number, because that is the form of g of z that we are trying to get, the sigmoid function. So given a number, can we return 1 upon 1 plus e raised to minus that number? So, and as a hint, you can also go ahead and look at the NumPy methods. If you have NumPy, we can do that. So let me go ahead and import NumPy as well. So I'm going to import NumPy as NP. And run this cell. Let's make sure that we have ran it. And let's come over here. And we can simply say return 1 upon 1 plus np dot exponential. Now that will return e raised to minus this number. Okay, as simple as that. Let's run this and make sure there is no syntax error. All right. And now what should be the form of y prediction? Now what should I write for y prediction? Yeah, it is simply sigmoid of mx plus b, right? Because in linear model, we had mx plus b over here. Now we want to pass this through a sigmoid function, which will transform our linear output and scale it to between, have a value between 1 and 0, right? So we can have sigmoid over here. And this will, we can pass the same mx plus b, just like we were doing before, right? Now, does everyone understand this? How did we get over here on y prediction is mx plus b and sigmoid of that? All right. So this was the most critical step. Remains this. Again, what will be the error? All right, is it getting better now? Okay, so what will be the error again? Just like we did yesterday. What did we use for error? Yeah, the predicted minus actual value, right? So again, let's do error equals to predicted y prediction minus y actual. Okay, and everything else, now what we did yesterday, we took the gradients and then we adjusted the m and b. We can have everything same on what we did yesterday. Okay, that doesn't mean the derivation of the logistic regression also follows the same line. Okay, if you notice over here, the cost function that we were using yesterday, now this was of the form, we were using the least square error methods. Okay, so we were using estimates minus actual the whole square. But if you try to do that, if you use the same technique over here, if you try to derive it, it won't work, because the output of your derivation, it will be a non-convex function. And a gradient descent algorithm, we can't work with a non-convex function, as I said before. So the derivation of that quantity will change, but the general form of implementation in terms of adjusting the delta m's and delta p, that doesn't change. Okay, so delta m, delta b, those things doesn't change. The way you derive it, or in terms of the cost function, that will change. Okay, but for the implementation standpoint, everything else remains the same for us. So let's go ahead and do the delta m, delta b, and let's come over here. Let's say delta m, just like we were doing yesterday. Delta m is, as I said, first we will say delta m is error times x, and then we'll multiply it with a small learning rate, right? So we need to multiply it with a small learning rate. So let's say if we multiply this by a small learning rate, and also should we move in the opposite direction of the delta m, right? We need to move in the opposite direction of what delta m is. So we can multiply this with -1. Okay, either you do this, or either you multiply this thing. This is yesterday's code, so I'm showing you yesterday's code what we did. So either we multiply this with -1, or you subtract it over here. So one and the same thing. Let me know if that is not clear. If you want me to stay consistent, we can use the same thing that we did yesterday over here. So just rewriting the equations over there. We are not doing anything new. We are going the opposite direction of the gradient. Then error over here multiplied with the small learning rate. Okay, nothing new, nothing, something that we have not seen yesterday. And then let's adjust m and b. M is m plus delta m, and b is b plus delta b. And then again, let's just return m b. Right now I don't need the loss as such, so I'm just returning the m and the b. Okay, let's see if we don't have any syntax errors over here. Okay, so it seems like it is working without any syntax errors. Let me know once you have completed the logistic regression method. All right, so now let's also call the logistic regression method. And just like yesterday, we'll do it inside a for loop so that we can do it. We can call this logistic regression method again and again. So this time I'm gonna do it several more times than what we had to do yesterday. Again, you can change the number of iterations and see how the kind of results that you are getting. So I'm gonna say for I in range. Let me make sure that you are able to see this properly. So for I in range, I'm going to say m comma b is equal to I should also have m and b over here instead. That will make sure that every time we run it, we initialize the m and b with zeros first. Okay, so m and b should be always 0 when you start off with this cell. Then m and b should be this can be 0, and let's say run this 100 times. Then m and b could be logistic regression. And then let's pass the x's, the y's, and the m and the b. Right? So this takes in all x, all y, the m and the b. So we passed in x, y, m, and the b. And let's try to run this and see if what do we get. Okay, so runs without any errors. So let's see what are the new values of m and b that we have got. So if I try to print out m and b, now these are the new parameters that our logistic regression model has learned. Okay, so based on the training data, these are the new models parameters that we have learned. We don't really know how this thing looks like, so let's go ahead and plot it on the graph so that we actually see what is happening behind the scenes. Okay, and if this thing does it make even any sense. Okay, so let's plot this curve on the graph on if m and b is 1.5 and minus 1.5, what does the sigmoid look like? We need to plot this and see how does, yesterday we were plotting a line and we were seeing how does this line look like. So today we'll plot that sigmoid, right? So over here, yesterday I had a method over here. I hope you have this open for you as well, yesterday's notebook. And yesterday we had this plot regression line method, a helper function that we built. Now today we want to plot a sigmoid on our screen over here. So can you modify this method to plot a sigmoid instead of the regression line? So I copy pasted it, what we had written yesterday, and now I want to say plot sigmoid, or I should rather say get sigmoid over here. Get sigmoid. It will return sigmoid. For x in x dot values, how will you modify this sigmoid dot append y. So you already know this. We have done this before in the logistic regression function. Can you tell me how to modify this line to instead get a sigmoid instead of a line? What should I change over here? Instead of saying y equals to mx plus b, to get a sigmoid, what have we done before? Yeah, simple as that. We just have to say sigmoid over here again, right? Because we have written this function sigmoid that transforms any number that we give it, and it will give a sigmoid of that, or the S shape, its position on the S shape curve. All right, so that will work. And now let's go ahead and plot it on the graph and see what do we get. So first thing that I'm going to do is first plot all the training data points again that we already have, right? So let's plot that on the graph. So I'm going to say plot dot plot x and the y, and let's plot it as circles over here because I want a scatter plot. And then what I could do is, let me also make sure that I give some titles and labels so that it is clear. Plot.x label is, we have hours, and on the y label I have the score, and then I can say plot dot plot. I want to plot the sigmoid as well. So what should I first, let's get the sigmoid. So I can say sigmoid is equal to, don't use the word sigmoid as such, because over here I'm using the sig over here because we already have a method over here which is named sigmoid. Now you might get confused, or you might end up using a wrong variable from your memory, because this sigmoid is a function, but what I'm referring to is a list of points over here. So this is the points in that sigmoid list. Okay, so this is get sigmoid, the method that we just wrote, and this method takes in the x, the m, and the b. So the x, the m, and the b. All right, and then you can do a plot dot plot of this sigmoid. So on the x-axis, again I have the x dot values, or again I have the x over here. On the y-axis I have the sigmoid, and now this time I'm going to plot it with a red color dot so that it is clear what is the sigmoid points and which are the points from the original data set, right? Let's say plot dot show, and let's see. I made a typo over here. Okay, so we are getting a sigmoid which is fitting our data points over here, and based on the learning rate that you have, you might get different shapes. So based on the learning rate, number of iterations, so let's say if I do only for 10 iterations, right? So if I do it only for 10 iterations, I'm not getting a proper sigmoid, and I'll end up using I'll end up misclassifying a lot of parameters as well, right? So based on the number of iterations that you have and the learning rate that you choose, you will get different shapes of the sigmoid. Okay, so just by looking at the shape over here, what's your intuition? Are we gonna get good results, or are we gonna make a lot of false positives or false negatives? So for this point, what will be a prediction? For blue point, what will be a prediction? will it be, yeah, it will be 0. And why is that so? Yeah, the again basic no fundamental rule that will apply over here as well is we'll use a threshold. Let's say this is a threshold 0.5 on the sigmoid curve. Okay, what we will do is try to make prediction. Right now what the red points is showing is our predicted values for each blue point. For each blue point, the red point is the predicted value of our model. Okay, and what we will need to do is we need to classify it into either pass or fail. So our rule will be, if the value of sigmoid at that point, if it is less than 0.5, right, it is less than 0.5, then we will classify our point as being either fail over here. If the value of sigmoid is greater than 0.5, then we'll classify it as pass. Okay, so can we write that method over here? Can we write that rule over here? Let's write the predict method, which will make the predictions. So let's make the predictive method. So define predict. Again, this takes in the X, the M, and the B, because we need to make predictions based on our input data and the model parameters that we have just learned, right? And that's why we need all these three things. Okay, our predict method, again, I'm just writing the same thing over here. We make the predictions based on our model, which is sigmoid of mx plus b, and our rule that we are going to use is, if y is greater than 0.5, then return 1, right? Else return 0. Okay, as simple as that. So all we are saying is, first take the sigmoid of mx plus b. The m and the b are the model parameters that we have learned using gradient descent. The gradient descent algorithm that we just wrote over here, the logistic regression, inside this logistic regression method. This is the gradient descent algorithm, and using that we learned m and b. And what we are saying is, if mx plus b is y is y is greater than 0.5, then return 1, else return 0, right? And if you want to see what our prediction is going to be on all the values of x that we have, we can simply do it using pandas as well. Or if you want to pass it one by one from a list of arrays, you can use it in a for loop as well. You can choose whatever way you want. Okay, so I'm just going to do it using a data frame. So I'm just going to create a new column in my data frame, call it as predictions, will be df.apply. I want to pass one row of my data frame at a time. So I'm going to say lambda predict, and I want to pass each row, each x one at a time, right? So I want to pass the hours and the m and the b to this method on axis 1. Again, guys, we have done this several times before. We have used the apply method to transform our data frame and make changes based on each value in our rows, right? We have done this several times before. So let's see what our prediction is. And after we have made the prediction, let's print out the entire data frame. Okay, so here's our predictions and the actual values printed side by side. Just by looking at it, are we doing a good job of making the prediction? So this is the pass is the actual output, and this is our predictions. What you could also do is just count how many times our predictions are equal to the actual values and also create an accuracy score out of that. But I'll leave that to you for you to try it out, and let me know if you have any other questions. We are already over time and we had a lot of glitches in our class today, so apologies for that because of the poor internet connection at my place over here. But apart from that, if you have any other questions about today's class, I'll be staying over here to answer any of them. If not, feel free to drop off. I'll see you next week. I'm going to stay over here and make sure that I have this thing open and you are able to complete this code. Yep, goodbye. And obviously you will also have it on your course page. The source code and everything will be posted over there. Goodbye. Goodbye, Manshu.